Okay, part 2 for this lesson 10.5. When differentiating a Taylor series, just take the derivative term by term. The radius of convergence of the derivative will be the same as the original series. However, the interval of convergence could change. Be sure to check the endpoints. So we're going to start off by looking at our function f of x equals 1 over 1 minus x. And if we looked at this as 1 minus x to the negative 1, and then took our derivative, negative 1 times 1 minus x to the negative 2 times the derivative of 1 minus x, this simplifies to 1 over 1 minus x squared, okay? So I'm thinking that possibly this function right here, in example number 3, is going to look something like 1 over 1 plus x. So if I took the derivative of 1 over 1 plus x, it's going to be, well, I've got my negative 1 over 1 plus x squared, right? Because it would be 1 plus x to the negative 1 power, and you'd bring the negative 1 down times 1 plus x to the negative 2 times the derivative of 1 plus x, which would just be times 1, so that would keep it negative 1. So we know that this function right here, this f of x, that it is the derivative of 1 over 1 plus x, but then times negative 1, okay? So it's only a negative difference of the derivative. So what we want to do is we want to look at what would 1 over 1 plus x be as a power series, because we know the power series 1 over 1 minus x is summation n equals 0 to infinity x to the n. So since this is the same thing as 1 over 1 minus a minus x, we can look at it as that summation n equals 0 to infinity of negative x to the n. So summation n equals 0 to infinity of negative 1 to the n times x to the n. So now if we take the derivative of 1 over 1 plus x, which we already over to the side, we know that that is equivalent to this, but we could find our summation by taking the derivative of that. So this is going to be summation n equals 0 to infinity. Remember that you're taking it with respect to x, and so this is going to be n times x to the n minus 1. Now, to get 1 over 1 plus x, we're going to multiply by a negative. So if we multiply both sides by a negative, and I've got a negative 1 coming in, getting multiplied there, and you could also write this, and I know that some of you, can see it pretty easily. It's not easy to explain, but you can, multiply it out and show that this is also equivalent to negative 1 to the n times n plus 1 times x to the n, okay? Getting rid of your n minus 1 and your n plus 1 on those exponents, okay? So both of these, it doesn't matter which one, okay? Now we have to use our ratio test to find our radius of convergence. So we've got our limit as n goes to infinity of the absolute value, and I'm going to use this first one just in case you don't really see the second one. I'll use the first one just to make it a little bit easier for you. So negative 1 to the n plus 2 times n plus 1 x to the n, because n plus 1 minus 1 gives you just x to the n, over negative 1 to the n plus 1 n x to the n minus 1. So that's your a sub n plus 1 divided by a sub n, right? Right. All right, so now limit as n goes to infinity, absolute value, this is going to be negative 1 to the n times negative 1 to the 2 times n plus 1 times x to the n over negative 1 to the n times negative 1 times n times x to the n times x to the negative 1. Okay, so you want to do that because you're trying to, figure out what will cancel. And you've got that canceling. Leaving us with, I'm going to move this x to the negative 1 up to the numerator. And you really don't need that negative 1 because it's going to take absolute value. So if you wanted to, you could just go that like that. But if you want to leave the negative 1, leave the negative 1. It doesn't matter. All right. So now n over n goes to 1. So this is going to be absolute value of x. Okay. So it converges when the absolute value of x is less than 1. So that means when x is between negative 1 and 1. So our radius of convergence is 1. Okay, which is what they were asking us for. All right, and now we have example number 4, Taylor series and integration. We can also integrate Taylor series term by term, right? We can also integrate. I should put the intonation on integrate because we just differentiated term by term. Now we can integrate term by term. Given that integration is the inverse operation of differentiation. So, example number 4, find a power series for f of x equals the inverse tangent of 2x using substitution and integration. So now, let's think about what we know about inverse tangent. Okay, so if we took the derivative of inverse tangent 2x, we're going to get, because the derivative of 2x is 2 over 1 plus, and then 2x squared would be 4x squared, okay? So also we know that inverse tangent of 2x plus c is the integral of 2 over 1 plus 4x squared dx, okay? So since we know that derivative, that means we know the next thing. Okay, since this looks like 1 over 1 minus x, we want to recall that 1 over 1 minus x is the summation from n equals 0 to infinity of x to the n. We also want to look at the fact that this in the denominator of, of this guy right here, 1 plus 4x squared, could also be written as 1 minus a minus 4x squared. So this would be like your x. That's not a division sign. I just kind of said, okay, the second thing, this is the first thing that we need to recall. The second thing we need to look at is, how do I write that so that my x is negative 4x squared. And then the next thing, well, it's coming, okay? Because I kind of am looking at my notes here. All right, so now we're going to integrate 2 over 1 plus 4x squared dx. okay? And this is going to give us inverse tangent of x plus c, right? But we want to integrate it using our power series. So if I pulled the 2 out and wrote this as that, this is the same thing as 2 times the integration of summation n equals 0 to infinity of negative 4x squared to the n. Because I just showed that 1 over 1 minus x squared is summation x to the n. So this one's going to be summation negative 4x squared to the n. So let's go ahead and do what we normally do here. We got to, take our negative 1 to the n. Our 4 to the n, I'm going to make 2 squared to the n, which is 2 to the 2n. Okay, I hope everybody saw that. I think you did. I don't think that's that big of a stretch, but the reason why we're doing that is because we got this 2 out in front. So let's go ahead and try and combine those at some point after we integrate, probably. All right, so now 2 times the integration. I'm going to go ahead and integrate. Sorry, I just drew my integration sign. Okay, 2 times. Okay, so we don't have to worry about anything like negative 1 to the n or 2 to the 2n. Okay, so when we integrate, we're going to have summation n equals 0 to infinity. We're still going to have our negative 1 to the n. We're still going to have our 2 to the 2n. But this is going to become x to the 2n plus 1 divided by 2n plus 1. What did I forget? Well, I can actually put my end this because my plus c, since my c is a constant, it doesn't have to be multiplied by 2 because it's just another constant, okay? So now I'm going to put my 2 on the inside of my summation. So this is going to become 2 to the 2n plus 1. And that oops. I mean, there's just one little silly, I think you guys can see it, but I'm going to go ahead and leave it, that is that, right? But then your constant, now let's think about that. That's what I was going to write over here. The inverse, if x is 0, the inverse tangent of 0 is 0. So therefore, your c is 0. Okay? So those c's are not going to matter. So what we end up with is that the inverse tangent of 2x is equivalent to summation n equals 0 to infinity, negative 1 to the n, times 2 to the 2n plus 1, times x to the 2n plus 1, divided by 2n plus 1. And that is using substitution and integration to find a power series for inverse tangent 2x. So that's your power series for inverse tangent 2x. The last series we want to develop is for a function of the form f of x equals 1 plus x to the k, which is called the binomial series. So if k is any number and the absolute value of x is less than 1, then 1 plus x to the k is equivalent to the power series summation from n equals 0 to infinity. That is k taken n times x to the n, okay? So that is what we're going to, and that's where the radius of convergence is 1. And it, it ends up equaling that, because that's your factorial definition, k taken, n times. So if n is 2, it's k times k minus 1, and then over 2 factorial. And then if it's, if our k is 3, it's 3 times 2 times 1. Okay. So, depending on what your k is, what power you're taking it, right? That's what you're going to be looking at. So they want us to find the Maclaurin series for f of x equals 1 over 1 plus x to the 4th. So for this one, your k is going to be -4, okay? So they've already told us that this is going to be summation n equals 0 to infinity. This is going to be -4 choose n times x to the n. So hitting that thing, I'm just going to put my 0 in. -4 choose 0 times x to the 0. That's 1. Minus -4 choose 1 times x to the 1. That's -4x. Plus, and then this would be -4 times -5 over 2 factorial times x to the 2. Plus, -4 times -5 times -6 times x to the 3rd over 3 factorial. Plus, dot, dot, dot. Okay, so now let's go ahead and simplify. 1 minus 4x plus, and if I take this, I get 20 divided by 2. This is going to be 10x squared. This next one, 20 times 6, this is going to be -120 over 6. So this is going to be -20x to the 3rd. Plus, dot, dot, dot. Okay, so that's your Maclaurin series for your f of x equals 1 over x plus, or 1 plus x to the 4th, which is a binomial series using that binomial series for k equal -4. So, could you have used that up here? Yes, you could have, but it's just we did it 2 different ways. Okay, so now, example number 6. We have approximate the integral from 0 to 1 x cosine x cubed dx to within 3 decimal places. And it says approximate. So the first thing we're going to do is find a power series. For y equals x cosine x cubed. Okay, we're going to recall, and this is another one that you need to have. This is a Maclaurin for cosine x. You're going to recall, and you need to have it on your paper whenever you're taking that AP exam, please. There's, like I said, there's a page in your book that you need to go to, and it's going to tell you, it's in chapter 9. It's going to tell you, it's a whole page of ones that they want you to memorize. And on a normal, year, I would have had you memorize these, but they're allowing you to have a piece of paper and have your notes and open book, but you want to know where it is. You don't want to have to hunt for it because you only have 25 minutes to do one problem, I think, or 20 minutes to do one problem and 15 to do the second problem. So you don't have a lot of time on that AP exam, and so you need to have all this stuff right at your hands, because a lot of times on the BC, they will put, some sort of Taylor series on one of those questions, one of those BC free response questions. And I'm going to give you some practice ones, so don't worry too much, but still you need to know what to do. Okay, so now from that we can get cosine of x cubed. So we can say that this is summation from n equals 0 to infinity, and this is going to be -1 to the n times x cubed to the 2n over 2n factorial. So you're putting x cubed in wherever the x is. And now we're going to simplify. So we got summation from n equals 0 to infinity, negative 1 to the n, x to the 6n, divided by 2n factorial. Now we can just multiply by x. So this is going to be x times that summation. And if we move the x to the inside, hopefully you can see that that becomes x to the 6n plus 1. And there is your power series, okay? Now, they want us to take the integral of the power series. So the second thing we have to do is integrate. Okay, so we're going to integrate from 0 to 1, x cosine x cubed dx. So that means we're going to integrate from 0 to 1, summation n equals 0 to infinity, negative 1 to the n, x to the n plus 1, over 2n factorial. No big deal. So that integration isn't that bad. Summation from n equals 0 to infinity, remember, you don't have to worry about that. You only have to worry about this x to the 6n plus 2, and then you're dividing by 6n plus 2, and then you still have 2n factorial in the denominator from 0 to 1. So summation from n equals 0 to infinity, you know we're going to calculate it with x equal to 1. Minus the calculation with x equal to 0. And of course, this goes to 0 because that's 0. Okay, so this is just going to be summation n equals 0 to infinity, negative 1 to the n, times, and really 1 to any power is just 1. So you really don't even need to write that, over 6n plus 2 times 2n factorial. So now, part 3. By, the alternating series estimation theorem, the estimate is at most the absolute value of the first unused term. So let's expand. And so we've got summation n equals 0 to infinity of negative 1 to the n over 6n plus 2 times 2 factorial is equivalent to, so if I put a 0 in, I get positive 1 over, and that's going to be 2, right? And then if I put a 1 in, I'm going to get a negative 1 on top. This is going to give me 8 times 2, 16. If I put a 2 in, I'm going to get positive 1 on top. And then this one's going to be 14 times 4 factorial. If I put a 3 in, I get I probably should have put minus. I get a negative 1 on top. Either way, though, not a big deal, but minus 1 over. And then you're going to get 20 times 6 factorial plus ... Okay, just kind of looking at what that's going to give you. So this is going to be 1/2 minus 1/16 plus 1 over 336. This right here, I want to see what that gives me. That actually gives me roughly 0.440, okay? The next term, if you put that in your calculator, you're going to see, so by the alternating series theorem, the absolute value of the next, that unused term, is going to be approximately 0.00007. Okay? So, what we end up with is, this means that it's going to be correct to 4 decimal places. So therefore, our estimate is correct to 4 decimal places. That means that the exact value and the estimated value are exactly the same for 4 decimal places, okay? And I know this is new, but that's what they're asking us. So approximate that to within 3 decimal places. Well, there it is. And I know that it's a good approximation. It's exactly the same for 4 decimal places. So that means it's exactly the same for 3. So this is exactly what that would give you, but